Thank you. I am what we call a glacial geologist, and that sounds pretty specific, but it's not. You know, if you think about it, I'm not a real geologist like many of you in this room, and I can see two, at least, who study rocks, who understand how rocks are formed in painful and minute detail. All right, that's not me exactly. I study the detritus at the surface. And this is what some of my cruder colleagues called glacial excreta. Right? This is just the junk that ice rips up from the landscape and puts down somewhere else. But it's not just detritus. It has a very long history itself, and it can tell us so much about environmental change. The processes, the reasons why, the timing, what happened afterwards, and all this kind of thing. So in many ways, glacial geology and its brethren in what we call paleoclimate studies, it's all about being a bit of a time detective. This is very much like an excellent detective novel. I draw on that analogy quite a lot, both in my classes and tonight, because largely it's been drilled into me. You know, we write lots of grant proposals, and sometimes it feels like that's the only thing I ever do, and it's full of this language which is supposed to make reviewers think, yeah, I want a review. I want to pay for this guy. I want to, fund this science, so I have to make it sound exciting. But really my goal for tonight is to, if we had a fireside and an armchair, it would be like that. This is, I think, quite an informal venue. I want to show you a bit about what I do and what I think we could do here. I'm excited to do here, but it would involve community buy-in. It would involve your interest and blessing and arm strength and things like that. Because these projects, they can go on for a long time. We can get a lot of information out of them. The public loves it, but it takes a lot of manpower. What we're looking at here is, where is this, do you think? Yes, Cuilcagh. Mm-hmm. Close, but a whole world away. This is Antarctica. Right, this is just a place sort of midway through the Transantarctic Mountains, and it's where I did all my postgraduate research, really. So glacial geology, starting in Antarctica, very exciting place. I like it because it's very much analogous to what it would have been like here in Ireland, not just 20,000 years ago, but on and off for the last 2.5 million years. So we have this great analog, and you can walk through this landscape and you're surrounded by boulders that have been dumped by an ice sheet that was bigger even than it is today. And as I'm doing that, I'm thinking, yeah, I've seen things like this at home. So it's great to have a modern analog. Who here has seen a glacier or an ice sheet? Don't be shy. I see. Oh, that's pretty good. About half of you, I'd say. Excellent. For the remainder, those who have not, they can be hard to visualize. You see them on screen, you'll see them here, but their scale is hard to imagine, and their convex nature, the way they dominate the horizon, they become the horizon. They very much become the world, and they're very wet, and they're very noisy, and they're full of rubble, and they move. Right, so all of these things make it very, very exciting to people like me. The reason I'm here is like Barney said. John had met me, and I met Gay B. Burns as well, over in the Cavern Burren. And there was a reason that I wanted to go and visit that place, but I knew nothing about it. And so here are two gentlemen who knew a lot about it. About the glacial deposits, about what people had done with them afterwards, and various things like that. There is a specific reason I came to Cuilcagh, which I've been mispronouncing this past 2 years, so it turns out. And I'll tell you why that is in a moment, but it all really starts with the Ice Age. So I study Ice Ages, and I also am just a tiny bit of background information, what we call a quasi-archaeologist, or a para-archaeologist, or just a fraud archaeologist. So I hang around with archaeologists, and they're busy doing their work. Usually with me it's in the tropical Andes. But they're doing the same thing that they do here, wondering, when did people arrive? Why did they arrive? Excuse me. What were they doing here when they got here? You know, what challenges did they face? What opportunities brought them here? And what happened to them? When did they start making their impact? These are all archaeologic questions that I become involved in. And I try to provide the paleo-environmental context, if that makes sense. All right, the backdrop. So a lot of my work is about providing the backdrop. And it could be the backdrop to people, or the backdrop to ecosystems and how they develop, or the backdrop to our own climatic experiment that we're running today. It all starts with data, and it all starts really with the Ice Age. There have been many ice ages. You probably already know that. The most recent one culminated about 20,000 years ago, and there are varying ideas about what it was like here in Ireland at the time. I think the most common idea is that it was just covered in ice, you know, kilometers thick, and you couldn't see any part of the island. And maybe that's true, and maybe it's not. Because there are computer models out there now, they're very fancy, they're very pretty, and journal articles being published all the time with these data, and they say, this is how it was, and you think, oh, grand, what was it based on? And if you look behind the curtain and you see that it's not actually based on a hell of a lot. And so we need more empirical data to say what these models, you know, are they realistic? Are they more than just pretty simulations? Because I need to know when the Ice Age ended, desperately. They won't fire me in Galway if I don't find out, but it would help if I did. And it pertains to global warming. Now, I'll get back to that in a moment, but of course it also pertains to humans, because humans couldn't be in here, in this valley, on this mountain, when it was still covered by ice. All right, so that's where the archaeology comes in. The Ice Age, we're talking extremes here. You know, this was a time when, as you can see in this admittedly fake image of Earth from above, this would be the Arctic in the Northern Hemisphere, and this is apparently what it looked like during the Ice Age. You know, we've got ice sheets everywhere. North America had the biggest ice sheet on the planet at the time, spreading into Greenland. We had the British-Irish ice sheet over here, which at some point joined with the Scandinavian ice sheet. Lots of ice, and then all the mountains outside the ice sheet, down the Appalachians, through the Alps, and across here, across this land bridge, they're all covered in ice as well. What happens when you take all that water out of the ocean and lock it up on land? Well, the sea level changes, doesn't it? So we're looking at a time when our coastlines look nothing like today, which if you are into your attention to detail, you look at this and say, hang on, that coastline is today's coastline, and it is. Okay, 120 meters lower, or 300 and something, 60 feet lower than today during the Ice Age. Very different geography. We'd be hard-pressed to recognize it, I think. Plants, animals, all these ecosystems, they've been rearranged, right? And the weather systems are all different. And there's not nearly as much carbon dioxide in the atmosphere because it's all been locked away in the ocean, sucked down there and not let back out. So it's a different world. It's actually quite a stable world in a strange way. Now we know how, I'm presuming, we know how glaciers and ice grow. Snow, lots and lots of snow. More snow gained than is lost, and then it just takes it from there. And so when I think about these landscapes, and I've driven through quite a few today, Connemara, interesting, very alpine looking, a bit like this, but minus the ice, and then through the flat, boring bit. No one's from Roscommon here, right? No? Truly? Oh no, we have one. There is an interesting part of Roscommon, and I found it today. But it's kind of flat. Okay, and then up to here, where it's a bit more monumental, isn't it? These big mountains, they remind me of Greenland. All shaped by the simple act of too much snow falling in a certain place and not being able to melt and disappear. And so, for a long time, this was my idea of the Ice Age in Ireland and England, where I grew up. And at times it would have been like this. But other times it would be more like this, when that mass of ice just keeps accumulating and accumulating. and burying the landscape and starting to not really care what the landscape is underneath it, because the definition of an ice sheet is, apparently, is that it can move uphill, downhill, across valleys. It does not matter. It's so thick and powerful, off it goes. And so think about Cuilcagh looking like this, just the top sticking out of it. A nun attack, essentially. It's a beautiful image, isn't it? It's a nice mental exercise to think about what it would have looked like. This, of course, it looks very cold. This is Antarctica, but really, our ice sheets were very, very wet, and this is important. We don't live very far north. This is not a polar environment. It never has been. And so even when there's ice here, think of it more like southern Greenland today, or even the Alps in a way, where you go there in summer and it's water. It's a land of water. It's running with rivers. Some of those rivers are torrents and you cannot cross them. This is taken from an aeroplane, and so these would be large rivers. This is the Greenland ice sheet in the middle of the summer thaw with lakes on the surface. So very, very wet. And let's see if this works. It starts pixelated, but it improves. You probably can't hear this because it's coming out of here. But this is Greenland today. This is Greenland in the middle of summer. And the memory I take away from this trip in 2014 is just waterfalls, noise, huge amounts of this mass being transferred from solid back into liquid and off to the sea. It's really kind of filthy, isn't it? It's surrounded by mud. Right? This is all waterlogged land and squidge and rotting snow. And so this is part of our Ice Age history as well. Lots and lots of water. And you can tell that because the way that the landscape around here is carved. Only wet, warm ice can do that. And the clay, I was learning today from Barney about the clay around here, under the fields, pretty much everywhere. This glacially derived clay, which they've used to make bricks. So a nice cultural link there. That, of course, is the stuff rich people pay for to put on their faces, and it is glacial flour. It's from ice with water underneath it, just grinding down the landscape and turning it into glassy flour and washing it into lakes and rivers, and eventually it settles out and becomes this glacial clay which we humans use for weird and wonderful things. So do think of the Ice Age here as wet as well. Not just frigid, but wet, dynamic. And then it all comes to an end. Now this is where I get really excited. We go from that to this. The Ice Age came to an end. The Earth's climate went from something fairly stable and cold, let's call it an ice house world, and it's been in that for 90,000 years, give or take a few warm blips in there, and it jumps out of that into something entirely different, into a new world, essentially. Same shape, but the seas have come up 120 meters, 360 feet. The atmosphere is now filled with carbon dioxide, which came pumping out of the Southern Ocean from its reservoir. The ice is gone. Right? You can see what we're left with here is basically a footprint of ice sheets, but they're gone. This is the biggest indicator that climate can change. And it happened recently, certainly in geologic terms. So the seas have come up, our coastlines have changed, ecosystems that have been around for millennia, tens of millennia, fragmented and scattered, dispersed, in some cases just destroyed. And we're in now a very stable, warm period. All right, this is called the last glacial termination, termination 1. And I find it fascinating because we still don't know what causes this. If you want to look at it in a boring kind of fashion, this would be one way of doing it. I don't have many graphs in this slideshow, thankfully, because I think graphs kind of get a bit tedious. But this is a very simple one. Sea level during the Ice Age is way down here because all that water's on land. And then by, say, 8,000 years ago, all of that water is now back in the sea. Those ice sheets have collapsed. The Ice Age is over. Okay? And we don't know why. We also don't be dragged into the misconception that this is what the termination looked like in terms of timing. Right? This is how long it takes the world's ice sheets to disintegrate and go into the sea. But that looks kind of slow to me. That doesn't mean climate did not change a lot faster or in more interesting ways. And that's kind of where this part of the world comes in. All right, so this is the end. This is where I come in. I'd like to just, for a little bit of context, explain what I mean by 90,000 years of ice ages. Here they are. This is taken from ice core data, so this is from Greenland, and the spikes are going back in time. And if you can't read that, it says at the far end, 450,000 years ago. All right, but this core does go back a long way. And everything up here is a warm period like today, and everything down here is an ice age. So not only are there many of these ice ages, and they do go back in time, 2.5 million years, it's also worth noting that the ice agey bit is a lot longer than the warm bit that we're in today, and also the transition between the two looks to be very, very fast. Okay? Exciting stuff. It means that climate change is rapid. Okay? Smoking gun kind of stuff, but we still don't know exactly what causes it. And this is the other 10% of the time, right? Cuilcagh looks like this instead. Our landscapes are taking a breather from the ice ages, from being scoured down and bulldozed and washed away. And humans come along, and we use the land in different ways. I didn't take this photograph, and it dawned on me the other day when I was putting slides together that I don't have any photographs of this part of the world. So if there's anyone in here who I plundered images from, you should feel honored. For me, this is a little bit like a trauma, a trauma surgeon. They wouldn't be very interested in dealing with an ingrowing toenail or something like that. And that might be what the Holocene is. It's kind of warm and it's stable. The Ice Age itself is cold and it's fairly stable. What a trauma surgeon wants is trauma. It wants change and stuff we can't predict or necessarily explain. The boy who comes in with an iron railing coming through here and things like that. Termination 1 is the trauma. It's the ripping of the world from one climate system to another. That's why I'm in good company when we start investigating abrupt climate change. It is like a detective story. Now, I've made that analogy before. I want to know why Earth's climate jumps the way it does, or why it shifts so massively. We know today why it's shifting. It's following physics. These are physics that have been known for 200 years now. Carbon dioxide is a greenhouse gas, and there we go. But before we started playing with the atmosphere the way we have, before the Industrial Revolution, we had these ice age cycles, and they're massive and very impressive, and we weren't doing it. And so the question is, what causes that? What made it happen? We're making inroads into that, but what you see here is a model, okay? It is not the truth necessarily. It's nothing to do with me. I'm not going to say it's right or wrong or good or bad. It's a recently published model. Do you remember that bit in the Holy Grail? When they're getting up to Camelot. It's Camelot. I think it's Patsy's. It's only a model. All right, we feel a little bit like that in the geologic community about computer models because they're awfully, awfully useful and beautiful as well. But they are not necessarily the truth. It's not necessarily fact. And the modelers would be the first people to tell you that. I think we just get carried away sometimes. But this is very interesting. So this is a recent, it came out this year, depiction of what a certain community thinks the height of the last ice age looks like. And glory be, there they are. So we are somewhere in here. So you can imagine this landscape just buried, right? It's all under ice, which extends way out into the sea somewhere. And this would be, say, at 15,000 years. So quite a bit later. And I don't know what you had in mind for when you thought the Ice Age ended, but according to this model, it's in Ireland, it's pretty much gone. Just pay attention to the the opaque white, not the faded, shaded stuff. And we are exactly where that red line is pointing. And so that is part of the reason that I ended up here in the first place, and this will be in 2021, was because this notion that this part of Ireland was the last part to become ice-free. So this is where the ice sheet died, finally. And so once the last piece of ice has gone here, you can basically say the Ice Age is over. But we need to explore whether this is true or not. All right? I suppose what's interesting to me, when we have thinking of it like a detective story, you need to have, well, time of death, right? Time of murder. When was the victim dispatched, approximately? Murder weapons? Yeah? Any witnesses or motives? And then what were them, how do they say? What was your motion at the time of the murder? Or where were you last night at between 6 o'clock and 9? Where were you 17,000 years ago in the summertime in Ireland? All right, these are the sorts of parameters that we need in a novel. And so geologically, we have the same thing. Not going to anthropomorphize it exactly. This is ice, right? It doesn't care. It doesn't have emotions. But here is something big and looks robust, and now it's fizzled out and it's gone. And we want to know why. Yes, that means it was warming up. Okay, but where did the heat come from? There's an awful lot of heat, and it's got to come from somewhere, released into the atmosphere. How quickly was this death by poisoning, or was it by stabbing, for example? Did the ice sheet wither away slowly and slowly, like the sea level record suggests, or was it gone like that? And what were the actions of everything else going on in the climate system of the world at the time? So what was greenhouse gas concentration doing? What was sea level doing? What was the sun doing? So on and so forth. And then when we have all those parts in place, we can start to say what might have caused this massive change in our climate system and what probably did not. Quick time check. Does that make sense? Yeah? Good. So the evidence that we have, because we do have these smoking guns, or at least we think we do, the evidence is geologic, okay? We have no ice cores here. We don't need ice cores. We need the rocks that the ice sheet picked up and dropped somewhere else. And I'll show you why in a moment. Rocks like this. This is the surface of the Antarctic ice sheet at a place called Shackleton Glacier. And the salient point is it's covered in rock. You know, this ice could be hundreds of meters thick. But it's quarrying pieces of the ground underneath it, and rocks are falling on from mountains and cliffs and so forth, and being transported. Because remember, this ice moves, especially when it has water underneath it, like in Greenland. All those rivers heading down to underneath the ice sheet, lubricating the bed, so they slide along quite rapidly. It won't run you over, but you could see it if you went back a few days, and you can hear it too. You can hear glaciers sending out these rifle crack sounds as they grind along. So this stuff is being moved and it's dumped off at the edges, and they're erratic boulders. You know, they're dumped at the edges. They say they are proof that ice was here, and sometimes, quite often in fact, if you have the edge of an ice sheet or a glacier that's fairly stable, it sits there for a few years, a bit like a conveyor belt, it's bringing all this material to the edge and it all falls down and it forms a ridge. It forms a nice ridge around the edge. And the ice can disappear and melt away and be gone forever, but the ridge will remain like a footprint of where that ice was. So we use this quite a lot. Glacial geologists like myself, we go looking for these footprints because they're evidence that the ice was here and it was this big and then it got this big and shrank, getting smaller and smaller over time. If we can find out exactly when that footprint changed in shape and finally disappeared, we have ourselves a climate record. And what that means for us on the ground is we have ourselves a record of environmental change. And if we can say when the ice disappeared from Cuilcagh here, we can say when did the landscape become available for people and vegetation and everything that we know it as now. So here we go, from rock on an icy surface to rock in the woods at the Cavern Burren, deposited in exactly the same way. So these are glacial erratics, and they are the basis for my work. Now, I was up on the hill this afternoon. I had 45 minutes to spare, so I'd never been up there actually. I've been to the Cavern Burren. I've been sort of halfway around with John Kelly. We drove up, and it was a very beautiful view, but I'd never actually been onto the ridge. And as it transpires, I found the boggy way up, and I found a very deep bog, which, you know, peat is interesting. Peat's its own climate environmental record, but I wasn't thinking about today about peat. I was thinking about rocks, and I was thinking about what can we see that? It's very nice and bright on my screen. It's a bit dark here, I'm afraid. But for those of you, you're probably all familiar with the area, right? So you know it better than I do. So this would be the summit here, and we would be looking southwestish, and there's the escarpment there, and I was plodding up the boggy way from the south. There are things up there, geomorphology, that get me hot under the collar, right? Forgetting the ice sheet for a moment, long after the ice sheet had gone, there's evidence that there are actually small alpine glaciers or mountain glaciers up there. Now, very, very small, but the kind of thing that you might see in the Swiss Alps. Locartona, for example, which I've picked out here with the white dashes, and there's the boardwalk going up. It is hemmed in by a very large moraine system. Remember, the moraines are the ridges of crud that form along the edge of glaciers and ice sheets. So that's interesting too, because there's no glacier there today. It's too warm, isn't it? But at some point between the Ice Age and the demise of the ice sheet and today, there was a time when it was not too warm, when summer was not too hot to get rid of all the snow that fell in the winter. And we had small glaciers forming there, and then those disappear and you have a nice lock instead. And then over here, can you see these little, yeah? And you can reference where you are from the summit up here. Does anyone know what I'm picking out here? It's on the cliff escarpment itself. And I get very excited about these.
A terrace?
No, it's not a terrace.
A little lake shore?
No, I don't think so. Think more dynamic. These things are great. They're collapse features. Yeah. And you don't see these every day. In fact, you don't see them at all. They're not very common. Yet you guys have them. You have at least two. And I think I saw another one around the corner here. Imagine, I was thinking, well, how do we ever explain these things? If Cuilcagh is like a Victoria sponge, a layer cake, and it is fairly horizontally layered, isn't it? And the ice is coming through and it's carving these escarpments very steeply, and they're very big cliffs. But the ice is not just eroding, it's actually supporting. And then the ice melts away because it's ephemeral. And so you've got this bloody great cliff, over-steepened, cannot support itself. And some of the layers inside this rock are weaker than others, and they collapse. Now, these are not the rock avalanches that, like in Yosemite, that go off and run away, but they are big collapse features, and they rumple down. Check them out the next time you're up there, or just looking on Google Earth, because this is the kind of thing that can turn into rock glaciers. These are indicators of permafrost and rapid environmental change. These are also what Geological Survey of Ireland gets excited about, because they are geohazards. All right, we need to know why these collapse events happen. And we can help with that. You know, we can actually figure out when these things occurred. Finally, nothing final about this at all. I'm going to talk about cosmogenic nuclides in a moment, but I don't have any pictures of your split rocks, Gaby, and I didn't take photos of anything but erratics that day. But this is basically to say that the cosmogenic toolbox, which is part of we'll call it a paleo-environmental toolbox, that I use and my colleagues in Galway use, and hopefully we will collectively use, does not just tell us about ice ages, it tells us about the people that came in afterwards. Okay, so this is from work in Peru. But similar to here, a marginal environment You know, the ice up there, the ice is just gone or it's still icy. People moved into that landscape. We have to get into their heads, inside these people's heads, to think, what were they doing here? Why did they come? And how did they find it? This, of course, is carved into rock. These split boulders, these, what do we call it? The boulder artwork. Rock art. Rock art, or even just people messing around with boulders. It has a geologic signature, and we can try to establish when they were doing that. And I say try because we have to be honest, you know, science is not, we don't know what the answer is, but we can test different hypotheses, and sometimes we get really good answers out of that. So this is absolutely worth a shot. What is it in rocks that allows us to be able to date them? Why is it that an erratic in the Cavan Burren, for example, or on top of Cuilcagh Mountain, deposited by the ice, can tell us when that ice disappeared, and therefore can tell us when climate was warming up and became too warm for ice to exist? This is a little bit like radiocarbon, but an awful lot sexier and newish. And that's why we're going to talk about it now. This is called cosmogenic surface exposure dating. Anyone heard of that before? Apart from John and Gaby? No? Good. Good. It means I can tell you anything I like and you'll buy it. The best analogy I can think of here in this dating technique is, say you want to find out how long your husband or your wife has been sitting out in the garden based on their sunburn. All right, so you truck them out there. Sounds like they're an invalid, but you put this person out there in the garden in the morning and you go away. And they're not sunburnt at all in the morning. And then, you know, they get sunburnt over time, but we don't know how long they've been sitting out there. So if we could take a sample from them and gauge how much radiation has destroyed their skin cells, and we know the rate at which skin burns in our other half, for example, then we can use that, the degree of redness, as a bit of a stopwatch. This is all about geologic stopwatches. Why am I talking about radiation? Because that's exactly what we see here. This is a supernova event. The radiation, cosmogenic radiation, that makes our dating technique work is nothing to do with the sun. It's all about these neutrons that are pouring through space from supernova events. And they're zapping through us all the time. You know, they're coming through this hall now. They go through our bodies. You may have seen them in YouTube videos. And I did have a nice idea to actually have a fish tank here and fill it with alcohol, gas, like a vapor. You know, you put smells like there's a medical clinic. And then you use some liquid nitrogen and you have a black light and it all becomes a little convoluted. But the long and short of it is that you can see the vapor trails made every few seconds as a cosmogenic particle comes zipping through, or cosmic particle. And they're from space. It's wild. What does that mean for us? When a rock is under the ice sheet, say it's been plucked out from a cliff and it's dark, you know, it's not exposed to the atmosphere, but it's plucked out and it's rumbled along, it's incorporated in the glacial system. It has never seen this radiation before, hasn't seen the atmosphere before. But as soon as that erratic is, here we are, a little schematic. As soon as that boulder pops out of the front of the ice sheet, say this could be right at the Cavan Burren, for example, or on this side of the hill, it's suddenly exposed to what we've depicted here as purple rain, but is really zipping particles. High energy particles, almost the speed of light. Okay? Just like we are exposed to sunlight and radiation. So it's a different kind of radiation. It's exposed for the first time, and the stopwatch begins. Why? Because rocks like this, they're full of different minerals. My target mineral of choice is quartz. Thankfully, because it's really, really common. And so let's say this is a bit of the sandstone that's up there, full of quartz. It's made of quartz. And so inside quartz, here, I'm sorry, the writing, the text is a little bit small, silicon and oxygen. That's what makes quartz. Okay, that's all it is. When it is zapped by one of these very high energy particles, the energy is so high that that particle cannot tickle the silicon atom. It smashes into it and strips some of the electrons off. It's a very, very high collision. The result is a nuclide of a very different flavor. All right, this all happens inside a quartz grain. It's kind of hard to imagine, but that's what this is depicting. So your oxygen becomes beryllium-10. Silicon becomes beryllium-10. Beryllium has 3 isotopes, I think, but beryllium-10 is the one we're interested in. It's not formed in any other way except through this interaction with cosmic radiation, which I find crazy. What I find crazy is the fact that someone knows this, that someone figured this out. Like woke up with a hunch that we should look for beryllium-10 in quartz today, and we found it. But it's in there. All right, so if over time that beryllium will keep accumulating inside your quartz because of this exposure, it doesn't change the quartz. This is very, very minor thing going on, but over time it's going to accumulate and keep accumulating until, for whatever reason, the rock is no longer exposed to the atmosphere. Happy with that? Yeah? So what this means for us then, if we can take a sample of that rock, and if we can get a load of quartz out of it, and then if we can measure how much beryllium is inside that quartz, we can calculate when the rock was deposited and when it first became exposed to this cosmic flux. Right? That's the very simplified version. What my student Ali here is doing is exactly that. She's smashing the top off some sandstones from Antarctica, made of quartz, just like the sandstone up there is as well. All right? And there's Gaby with one of our boulders that we sampled in 2021. And the same thing has happened there. Quartz is our chronometer. And all weird and wonderful things happen to it next. Because think about this. It's a bit like a recipe. And I love it because you end up with data, but you start with what I gathered today in the interesting part of Roscommon, which is a chunk of rock. Right? This is my sample. So just like our Cavan Burren samples from last year, you can look at that. It's made entirely of quartz. So I know that it has cosmogenic beryllium-10 in it, and that's going to be very useful for me. And now starts the fun part. You have to separate it. You have to convince rocky minerals to disaggregate. And that takes a lot of chemicals. All right, so what we're seeing here in our lab is we're boiling it in phosphoric acid. That's the same stuff that's in soft drinks, incidentally. But these things help eat away at the cements that hold these grains together. And they help eat away at some of the metals as well. It makes you think what else it's eating away when you drink those things. But that's just crushed up sand, that's crushed up rock. All right? It's a very long video. So we've got rid of other things. Now we just have quartz. There's no more feldspar, there's no more mica, none of that junk, because we've burnt it away or we've separated it with these amazing heavy liquids that allow certain minerals to float and others to sink. All right, and we're left with pure quartz. But the beryllium is still locked inside it. The pure quartz looks like this. All right, here's a bag. You can even pass it around. This one is from Colombia. I'm not joking. That's from the Sierra Nevada del Cucuy in Colombia. A beautiful place made of rocks similar to Connemara. But that has been purified, so everything else is gone. So it's just quartz, and it looks like cocaine. And you try taking that to the US, where I take these to my lab over there. And no one's ever said anything, actually. But you have bags and bags of them. And if you snorted that, it would kill you in a different way. So what's happening there? All that sand has the beryllium inside it. Now we need that. So we say goodbye to the quartz. Quartz is a very hard mineral. And so what you're seeing in this beautiful soporific video is a little convection going on here, because this is hot, concentrated hydrofluoric acid. Right, so this is the nastiest of the nasty. not hydrochloric acid, but hydrofluoric acid. This kills you if you get a splash on you, and such, things like that. But they try and scare us in these lab videos. It's good to be scared, but also not too scared, otherwise you'd be jittery as you try and pour this stuff in. But it dissolves the quartz. It turns it into a liquid. All right, so our beryllium is now free. I'm not a real chemist, but I was told by the person who trained me in this. She said, well, do you like baking? I said, yeah, I like baking. Can you follow an ingredient list? Absolutely. Then you can do this. And that's my kind of science, because it's chemistry, and someone thought of it, but you don't have to think too hard. You just have to be very, very clean. All right, contamination is the problem here. All this wizardry, this time machine, it just depends on you following the book and not being dirty. What do you see here? Well, we're now stripping things out from that liquefied quartz, because there is a trace amount of other stuff, like a bit of titanium and calcium and things like that we do not want. And so, anyone done anion chemistry or anything like that? That's all you see here. It's resin, fine microplastics really. And let's just see that again. So I tip the sample in very, very carefully. And what you see here migrating down the resin is a red band. And that is all the titanium that was in our quartz. And all the quartz has it. And this strips it out. And so that red band is titanium being sort of eluted away. It looks like someone's having a very bad day in the urine analysis over here. But it's a great sign for us because it means we've got rid of that. And finally, we've gone from a giant, great big rock to sand to what you can't even see in here, but this is a Bunsen burner-y thing, a tiny pellet of beryllium. And the beryllium is turned into beryllium oxide, and that little thing there is a cathode, and there it is, one of these, with the world's smallest hole in the end, which is just, anyone can play with this, it's just big enough to get a microgram or two of beryllium powder in, which in itself is apparently very toxic, and you tap it in with a drill blank, tap, 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 send it off to California, and they have a very big fancy machine, and this is, I think, what they have in Belfast, Queens. But I work with a California lab, I have and will continue to. It's very good, and they zap it with an ion beam, and that ion beam basically it burns it up. And it can tell us, the gas that comes off it, it tells us the ratio of beryllium-10 to beryllium-9. And the long and short of that is we get a number. We get a ratio finally. And so we can actually, with that ratio, calculate how many years this boulder has sat exposed to the atmosphere. Yeah. And so this is a real age. This is the first time it's ever been shown. Notice the plus and minus on here. So whether it was a bank holiday that this was deposited on, we won't know. But that boulder, if you go back, the moss has probably grown over it now, but there's a little scar on the top where we took a tiny piece of, tiny flake basically of rock, and the result is this age. It was deposited 15,775 years ago. So let's just say 16,000. That's pretty cool, I think. Right? This is a geologic stopwatch with which you can do a great deal. Is that enough to seal the story? To say, this is when the ice sheet disappeared? It's not. Because this is science and it's full of errors, okay? And we need statistics. And so what we actually did is we sampled, I think, 6 boulders that day. And we need to run all 6 from that one site, because machines, they wave, they wobble like this, and they do it somewhat predictably, but where you measure your sample, you could get a different ratio. Not wildly different, but my point is we want to run 5, I suppose, and then you can look at the statistics. They should all be basically the same. You can get the mean age of that, and that is the most scientifically robust way of doing this. But it's an excellent first stab. I was delighted because this boulder looks perfect. It's even sitting on a limestone pedestal. Perfect in the sense that it doesn't look like it's moved. Because imagine if you're running the experiment with your spouse and the sunburn, if they went in halfway through the day for an hour's kip inside, that would screw up the experiment, right? That's time not accounted for. Or if someone turned the spouse in the chair to face the other way, away from the sun. You know, if these boulders had been tampered with or fallen over or buried by peat bogs, right, real problem here, then that cosmic radiation cannot reach the rock and our stopwatch becomes a bit funky and the age could be too young, right? So that's why we need quite a few of these samples to say, nope, this is the real deal. Now, what this means for humans is I'm dating glacial rocks here, but you can also date quarry faces. You could date, if you knew where, say, Stonehenge rocks came from. I don't think they have any quartz in them, but if they did, you know, you can go to the escarpment from the quarries. You can date those when they were exposed, not by ice, but by people. Or the pyramids and the rocks to make those. You know, any sort of human endeavor that involves moving rocks and exposing faces, like splitting boulders, for example, in the Cavern Burren and elsewhere, could be explored with this process. Because it's called surface exposure dating. And so if you imagine this erratic has been exposed for 16,000 years, and then someone comes along thousands of years later and somehow splits it in half, you're going to expose new faces, aren't you, to cosmic radiation, and they will have a different time stamp on them. Okay, this is the sort of thing we can do, and all it takes is a hammer, a chisel, a fancy lab, and a little bit of money. Everything comes down to money. Now, I realize time is coming on a wee bit. I'm not looking at the watch on purpose. What I'm proposing to do here on Cuilcagh and surrounding area is really reconstruct the demise of the last ice age. Okay, that's my personal passion, right? I want to know, first of all, was this mountain a non-attack? Did its summit stick out above the ice sheet? That's very important because these models have different thicknesses. Some say kilometers and kilometers thick, in which case there's no way this mountain was sticking out. Others say, no, it's actually quite thin, and these mountains were sticking out. These are very academic arguments. It's like two bald men fighting over a comb, as someone has put it to me. But it does matter, because A, it's interesting, and B, it's how we forecast sea level rise. Because you know the Earth is always rebounding from the ice age, isn't it? And depending on how much ice was there in the first place, that dictates how much it will rebound. And so we can figure that out with erratics taken from the summit of Cuilcagh Mountain. We can figure out how quickly it thinned, you know, down by taking erratics down a transect. We can say, did it happen very, very quickly, or was it gradual? That's very important for me because that's a period, I didn't mention this before, but it's a period of what we call abrupt climate change. It looks like some of these warming events happened in a few years, like literally less than 10 years, like a massive warming. If that's the case, then that should be registered in the ice. And we currently have absolutely no idea how quickly this ice mass over Ireland took to die. I want to find out how old those little Corrie glaciers are under the escarpment, because that, as I said, is another time when the climate was very different from today. And it may not have been for very long. It may have been just 100 years or maybe 1,000 years. We don't know. But it pertains to what's happening in the North Atlantic Ocean. And our detective story can get us nowhere. It's just idle speculation and, you know, suspicion until we have dates and numbers. Because then we can compare what was happening up there with what was happening out there in the sea. Those rock avalanches, the split boulders, you know, this is where we want to bring this new technology into the human realm. Complementing that, we also have these wonderful coring apparatus, I suppose we would call it, because what I noticed today is there's a lot of peat around and a lot of lakes. And lakes that used to be lakes but are now mires and bogs. And all of them have a very rich sedimentary archive in them, which we can extract. All right? And that's what we're doing here. This is the Galway's, we should call, I don't know, It should have a name. I realized today it doesn't have a name, this mighty ship of ours, which cost 100,000 euros long before my time because it's made of titanium. But it's great. It's this great big floating platform. And you can send, what's happening on here is you send down coring rods with a titanium barrel on the end of it, 2 meters long, piston corer thing. And the fruits of that labor on the table behind us. We can have a look in a mo. And we just keep punching down through that layer cake that's on the bottom of the lake, bringing the sediments up sequentially and extruding them into these beautiful sediment cores, because everything that happened on this landscape is preserved in these sediments. We just don't think about it when we say you're paddling around in a lake and the mud is at your feet, or, we don't think about we are disturbing an archive. What sorts of things are in here? Well, the first plants. The first plants to arrive on a landscape, fragments of them are in here. The first insects. And those insects can often tell us about climatic conditions, environmental conditions, like what were summers like, what were winters like. There's chemistry in there. And a lot of chemistry, we can actually work out weird things like how seasonal was it then? Let's say in the time between 16,000 years ago and now, how has seasonality changed? What do I mean by that? Well, right now we don't really have much seasonality, do we? Not thermally. It gets dark and it gets light throughout the year, but it's all pretty much the same temperature compared to someone, say, living in Canada with ferociously hot summers and ferociously cold winters. That's really seasonal. Here, not so much. But it has changed in the past, we think. And there's evidence again for that on the table behind us. And it all comes out of these tubes of mud. And when people start entering the environment, I'm not saying that we find arrowheads and things like that in these sediments, though there's always the chance. No, we find discrete signatures. Like when people first start to impact their environments, they're bringing parasites, maybe their own parasites or parasites associated with livestock, cattle and things like that. Charcoal, even tiny amounts of charcoal from land clearances. You start to see these in the sediments, and it's all in there. All right? And so not only could we address these split boulders at places like the Cavern Burren, that's like direct hypothesis testing, we can also look on a forensic scale in the sediments to see what, if we can see when people first arrived. I will leave you with the thing that pops into my mind, and it has done for a while now, and it was reinforced when this age came back from the Cavern Burren, that 16,000 year one. 16,000 years ago, fine, Ireland becomes ice-free, by and large. When did people arrive on this island? Shout out some numbers. 10? 9 to 10, okay. Anyone else?
7.
Okay, 7. I don't have an answer, by the way. I'm interested because I want to know what people know or think we know. Okay, fine. So that would be a gap of as much as, let's say, 8 to 10,000 years after the ice had gone. Yet there were people over in Britain during the Ice Age, hanging around on the southern margin of the ice sheet and following it back as it retreated. And you can see Ireland from where I grew up. And everywhere else in the world, people seem to say, ooh, look at that, I'm going. And they go. Even when they can't see it, because it's on the other side of the Pacific, they go. And so I'm not saying people were here earlier than you're suggesting. I'm just saying, why not? Why did they not? If they did not come until much, much later, there's a reason. And we should investigate that. These are long-standing problems that will take a long time to understand fully. But we do have the tools to make inroads into that. And this is, in my mind, the best natural laboratory that you could ever ask for. So on that note, I'll stop prattling on. I'm not going anywhere, so I'm happy to chat and take questions and look at the cores behind you. They're very exciting. And we can have some lights.
Lights?
Yeah.